Think, learn, innovate.
Hi everyone. Today our topic is Maxwell-Boltzmann statistics. It is an important part of our statistical mechanics and is present in your physics courses of engineering first year all semester. And by starting first of all with Maxwell-Boltzmann statistics, I must explain to you guys the basic postulates of your Boltzmann statistics. Number one is that the particles are interacting, they are identical, and they are distinguishable. Like, consider a chalk. Okay, you have a white colored chalk, blue colored chalk, red colored chalk. All chalks are identical, but because their color is different, they are distinguishable. Number two, they do not obey Pauli's exclusion principle. That is, that each quantum energetical state can accommodate any number of particles. Say one state can accommodate 2 particles, 3 particles, or n number of particles. And number 3, the particles are spinless. Now, in here, what we will do, we will establish or we will derive the Maxwell-Boltzmann distribution law. Maxwell-Boltzmann distribution law. Okay. To do this, finally we'll find out the partition function. And so what I will do, first of all, I will introduce that there is an n number of total number of particles present there. So I will say let n number of, so in this case it will be distinguishable particle, distinguishable particles. So there are n number of distinguishable particles. So this n number of particles, what I will do, we'll consider this n number of particles by writing down in this form. Say it may be n1, n2, n3, ... I will say let the final number of particles be n. Okay, similarly, the particles have energies. The particles have energies given as, so I will number the energies to be, say, E1 for N1 particle, E2, E3, and it will go on and it will be finally given as En. Okay. So these particles are distributed. These particles are distributed. So they are distributed in say in quantum states. Quantum states given as, say, G1, G2, G3, Gn. So till now what we have done, we have find out the number of particles, energies, and what we will do, we will have found out the states. Now we'll go to the next page, and what we will do, since this energy E is associated with n number of distinguishable particles, so we can write down this equation in this format. So I can write down that the energy particle N1 have energy E1 plus particle N2 has energy E2, and so it goes on, and the last of particles is N has energy En, and so the overall I can represent this one in a sum series that given as I equal to 1 till n, and it will be Nn and En, and if I take all of them together, I get a constant value of energy E. Similarly, the particles can be summed up in this format: N1 plus N2 plus n3 dot 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 dot, it is nn, and that can be represented as sum of I equal to 1 till n into ni, and it is n ei, ni and ei, so ni, and it is given as n. Okay, so n is the total number of particles and this is the total energy. So from here we can write down the distribution function of this Maxwell-Boltzmann distribution law. What we will say, let us consider that G1 is the probability of location of a particle at certain energy state EI. So Gi is the probability of location. Gi is the probability of location of a particle with energy EI. Okay. So probability of two particles, how if it's two particles, I will write down Gi into Gi, it will be Gi square. Okay. In the same state actually. Therefore, the probability of n number of distinguishable particles in state Gi is given as, therefore, what I will say, the probability of ni number of distinguishable particles to be distributed in Gi states is given as Gi to power of n. So when I got this, hence the whole probability distribution function, hence the distribution function is given as, I will say the distribution function is W, and this distribution function is equal to total number of particles present here and the product sign of I, what I get, Gi to the power of ni divided by ni factorial. So this is your overall distribution function, and this one is called product actually. Okay, now what I will do, I will solve this one. To solve this one, you know, this is a probability distribution function and I have to take log on both sides, so I have to use few tools. One of them is your Stirling formula. So now I will solve this distribution law. To solve this distribution law, I will use a Stirling formula. So I will use Stirling formula, which is given as like ln A factorial will be written in this form of n A ln A minus of A. So this is your Stirling formula. So what I will go back and I will write down my distribution formula just before, which I have written now. Product I equal to 1 till n Gi to the power of ni divided by ni factorial. Now what I will do, I will take log on the both sides, ln W, and it will be ln factorial n, and it will be plus of this product sign will be put into a sum sign here, and it will be ln Gi minus of your I equal to 1 till n and ln ni factorial. So what I will do now here, I will use Stirling formula, this formula here and here. So my formula will now reduce to ln W is equal to n ln n minus of n, and I get plus of sum equal to I equal to 1 to n ni ln gi minus of what I get here, factor sum equal to I equal to 1 till n, and I get ni ln ni minus of ni, like this. Now remember, the sum of ni is equal to total number of particles, that is n. So I can write down this one in this format. Ln W is equal to n ln n minus of n, and I get plus of sum equal to I equal to 1 till n, ni equal to ln gi minus of sum of I equal to 1 till n, ni equal to ln ni plus of sum of I equal to 1 till n equal to ni. Now this whole thing is equal to n. So this n and n goes away. So I got ln W is equal to n ln n minus sum of I equal to 1 till n, ni equal to ln gi minus of sum I equal to 1 till n, ni ln ni. Now the most probable distribution can be obtained by evaluating the maximum value of ln W and then square it to 0. So differentiating, now what I will do now, I will differentiate the above equation with respect to ni. So I will differentiate this whole equation with respect to ni. So I get d ln W, and I will get d n ln n. What I get here is I equal to 1 till n, dni ln gi, and minus what I get here, first of all, I equal to 1 till n, dni ln ni minus sum of I equal to 1 till n, ni into 1 by ni into dni. This goes away, and this one will be 0. And similarly, TLW, I will keep the D ln W, and this one, what the equation will now become is I equal to 1 till n, dni ln gi minus sum of I equal to 1 into n. What I get, dni ln ni. So I got this equation here. So I have this equation now, and I will try to solve this equation. And what I will get here, see, dni is common. So I will go to the next page. So I get d ln W. So if I go back, I got ln gi minus ln ni, gi by ni. So I will go back, and I will say, okay, it's the sum. I will sum of I equal to 1 till n, and I will say dni is my common. And what I got here is gi minus of ni. Oh, sorry, ln gi, and here, so it's better to write down again. So it will be, say, ln gi minus ln ni. That's I get from here. So I can write down this equation in this format. And so for what I will get here, now what I will get here is I can take this one, d ln W, and I can write down this equation in this format to simplify it, and it will be easy for me to do the further calculation by saying ni by gi. So it will be ni by gi, and I will take minus 1. Now you know the derivative of ln w, it will be 0. So what I get from here is I equal to 1 till n dni ln. So again, let's write down nicely. So here I will write ln ni by gi dni equal to c. So I got this equation out after solving the overall your distribution function. Now, few minutes back, we have seen that sum of I equal to 1 till n ni ei was my total value, which I can write down as a constant value. And this constant can be even this constant value. And so if I derivative this value, derivative with respect to what I told you a few minutes back, I have dividing all of them with respect to ni. So if I do the derivative of this I equal to 1 till n dni ei will be equal to 0. So this one, if I multiply with any value, this side and this side, as it is 0, it will be always 0. So what I will do here is, I will multiply this whole equation by a value called beta. And so if I do that, I will multiply this one beta. And if I multiply this one with beta, what I get? I get sum of I equal to 1 till n beta ei dni equal to 0. Now similarly, a few minutes back what I've told you guys that I equal to 1 till n, what I get ni is equal to total number of n, that particle is constant. So I can write down I equal to 1 till n dni is equal to 0. Here also, if I multiply a number with the 1, 0 into that will be also, if I use alpha here and I multiply alpha here, so again I get another equation I equal to 1 till n alpha d ni, that will give me 0. So I got this equation. This is a very important one. I got another equation here. And I got this equation. Now, see the 0 is here. So, if I add 2, 3, 4, 0, nothing will happen. And in this 0's case, I can plug in the values of these two equations there. So, left hand side, I have this equation. That's okay. And on the right hand side, what can I do? I can add these two equations there, because these two equations will give you the same values here. So see, this minus sign I have taken 0 here, or I can plug this minus sign back here itself. This is equal to 0. So as it is 0, I have taken this minus sign off. Otherwise, I can keep it down here like giving this minus sign. So go back to the next page. What I will do here is, I will start the solution again. I will say, okay, it's given to me I equal to 1 till n. Say minus here. And what I got ln, my value was ni by gi into dni, which is equal to 0. And that 0 is nothing else, sum of I equal to 1 till n. And what I got beta ei d ni, and what I got here alpha sum of I equal to 1 till n d ni. I got this two equation. So again, what I can do is I equal to 1 till n ln ni equal to gi divided into dni, and I can write down here sum of I equal to 1 till n, and I can say beta ei plus alpha, and what I got? T Ni. If I bring it in one place together, it gives me I equal to 1 till n, and what I got? ln ni by gi plus alpha plus beta ei, and here what I get here? D ni equal to 0. So if this is 0 and there is independent variables here, so what I can write down here, I can take this value is equal to 0. So I can write down n of ni by gi equal to minus of alpha plus beta ei. So ni by gi equal to e to the power minus alpha plus beta ei, and or ni equal to gi e to the power minus alpha plus beta ei. So here I got the values of ni with respect to gi e to the power like this. This equation is called Maxwell-Boltzmann distribution. This equation is called Maxwell-Boltzmann MB distribution law. Now, actually, I can resolve this one more, means I can go a few steps forward to solve it more by saying that, okay, I will solve this one by stating that, okay, I got my value here as ni equal to gi e to the power minus alpha plus beta ei. Okay, and this alpha and beta are physical properties of the system, and so these n particles, how can I write down these n particles? Actually, this ni actually gives you the total particles. How can I get the total particles? Few minutes back I've written down n equal to n1 plus n2 plus n3 and dot 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 like this. So my total n, first n, if I plug in g1 e to the power minus alpha plus beta e1 plus g2 e to the power minus alpha plus beta e2 plus g3 e to the power minus alpha plus beta e3, and it will go on like this. So now what I will do here is I will say n is equal to what I can take a common outside here is e to the power minus alpha. You see, I will take the common from e to the power minus alpha here, and then I can write down this equation e to the power minus of beta e1 plus g2 e to the power minus beta e2 and plus dot 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 dot, it will go on like this. So here I can write down e to the power minus alpha, and I can use a sum series of I equal to 1 till n, and it will be gi e to the power minus beta ei, and this one, this whole thing, I will name it as z, and it will be my partition function. It's called partition function. Now one more thing here is that this alpha and beta is where what I told you that it is it's always referred to as a system parameters, and this system parameters is very important in future calculations actually. So I will write down the value of beta here for the configurations, and it is V by kT. K is Boltzmann constant and T is absolute temperature. And I can write down my alpha also, alpha equal to minus EF by KT. So hope you liked the video, and I will bring more other video like this because many of students has told me to to a video like this so that they can understand the derivation of Maxwell's Boltzmann's distribution law. So if you like it, please share it and have a nice day. Bye.